And now for a look into the future with the GOES-R platform, which should be around in about 2017. A suite of GOES-R products will detect and monitor volcanic ash as well as sulfur dioxide, which often is co-located, sometimes not. We saw that with ash in the volcanic clouds. Current GOES operational volcanic cloud products are qualitative, primarily due to sensor limitations. Improved spatial resolution and a large selection of spectral channels will enable GOES-R ABI, or Advanced Baseline Imager, to generate more advanced quantitative volcanic cloud products. The SO2 detection product will automatically detect volcanic clouds during very early stages when an ash signal is generally obscured by liquid water and ice. The Volcanic Ash product will provide objective estimates of ash cloud coverage, height, mass, and particle size, which are necessary to issue SHyMets in the case of advisories for aircraft, and accurately forecast the dispersion of the ash clouds themselves when put into models. The GOES-R volcanic ash and SO2 detection products will be generated from infrared radiances, which are day-night independent. ABI channels centered at 7.3, 8.5, 11, 12, and 13.3 micrometers will be used in all the algorithms, with the 8.5, 11, and 12 micron channels providing information on cloud particle size and composition. The 13.3 micron channel will detect ash cloud height, and the 7.3 micron channel will detect SO2 clouds. These algorithms are unique because they account for background conditions such as surface temperature, surface emissivity, atmospheric temperature, and water vapor on a pixel-by-pixel basis. Consideration of background conditions results in greater sensitivity to thin ash located in the atmosphere and consistent algorithm performance from the tropics, where you can have water vapor problems, all the way up to high latitudes. You get that consistency all the way across. So in a nutshell, here are some of the benefits from the GOES-R volcanic products yet to come. The advanced spectral, spatial, and temporal resolution of a GOES-R Advanced Baseline Imager will be utilized to generate a complete set of volcanic cloud detection and monitoring projects, resulting in improved air and ground safety as well as economic savings. Also, the GOES-R products will be used to improve modeling of volcanic ash clouds, which will allow for more accurate cloud dispersion and ashfall forecasts. Here are two good examples of future GOES-R volcanic ash products based on the eruption of Mount Redoubt back on March 23, 2009, brought to us by Jim Gurka, Steve Goodman, Mike Pavlonis, and Gary Hufford. This example actually simulates what we would be getting with the GOES-R platform in the form of ash loading here on the left, which is critical. We must know the concentration within the atmosphere and where it's located horizontally, with ash height here on the right, showing the relative locations within that horizontal view and where the ash is located. This is critical for being able to fly aircraft in and around an area where a volcano is currently erupting and getting them in and out of around an area safely. And now we come into the realm of synthetic imagery, or synthetic forecast imagery, which was born out of the GOES-R program, which will become operational near the end of the decade. Here on the left, we actually have a synthetic image generated from cloud models within the WRF model platform. Here on the right is the matching real-time image from GOES 13, and you can see great similarity between the two. The idea here was to be able to actually model cloud fields through and give you an idea what it would look like on the satellite platform through using model forecasts themselves. This is quite unique and looks very different from what we see now. Here's some of the motivations and goals, but down here one of the main goals was to aid in the development of algorithms aimed at aerosol retrievals, which included smoke and ash, and of course ash from volcanic eruptions. So what are we going to get with the new platform, new GOES-R platform? Well, currently we have 5 bands to work with. The visible is approximately 1 kilometer in resolution. we get about 4 images per hour. Routinely, we can get more than that if we call RSO. And we don't have any visible reflective bands as on-orbit calibration. But with the new GOES-R platform going up later in this decade, we're going to have 16 bands to work with. Our visible resolution is going to be a half a kilometer. Infrared is going to be 1 kilometer, which is what the visible is right now, which is pretty darn good. We'll have 4 full disk images 4 times per hour, and routinely we're going to increase that to 12 per hour, so that's every 5 minutes. So that's what we get with RSO right now, but that'll be our routine numbers. And on a mesoscale level or scientific level, we can get images every 30 seconds if needed. How is synthetic imagery created? Well, first we input numerical cloud models such as RAMs, WRF, or coamps. We can use the microphysics from these. And then we run the cloud model and use the output as input to generate the synthetic GOES-11, GOES-12, or GOES-R in this particular situation, satellite observations that we would see at different channels. This product is a combined effort between the National Severe Storms Laboratory in Norman and CIRA, Cooperative Institute for Research in the Atmosphere here in Fort Collins. Daily output from NSSL's 4-kilometer WRF ARW model is provided to CIRA, who then generates the synthetic satellite imagery, which is then sent back to the Storm Prediction Center for their use. Every day at 0Z, NSL runs the 4-kilometer WRF. As soon as the 12-hour forecast is completed, several variables are extracted and sent off to CIRA. These variables include temperature, water vapor, and other physical and microphysical parameters which are needed for the next step. When all the variables have been received at CIRA, an observational operator is then run to generate synthetic imagery for GOES-R ABI bands, and there are 4 of them that we use right now, and this is if we're generating the synthetic GOES-R imagery. The simulated imagery is then converted to Mercatus area format files and made available back to SPC, who then makes the output viewable on AWIPS. Hourly output between 12Z and for the next 36 hours is processed and available for SPC to use. This product has 2 primary purposes: to generate synthetic imagery from cloud model output that can be used to evaluate each model run. For example, one might compare a simulated water vapor band to observe GOES imagery from, say, between 12 and 18Z, and you match those up with what you're actually seeing in the 12 to 18Z time period and see how well they match up, and that gives you a good idea how well the model initialized. And 2, since the simulated bands will be used on GOES-R ABI, and this is what we'll be looking at in the future, it's good training for getting an idea of what we'll be able to see at that time, and good research and for now to find out what we can do with all these extra channels that we're being given. Here's a quick look at 12 of the 16 bands that we'll be privy to on the GOES-R platform when it comes. This was actually run for an earlier period back on May 8, 2003, a severe weather day in Kansas and Missouri, just to give you some kind of an idea of the different look at the different bands. And remember, too, not only do we have just the bands themselves to look at, which we can see a lot of them look very similar to each other, but we will also have the ability to difference or combine a lot of these together in different ways to come up with different looks, and some of those have yet to be determined. So this is why we've been talking about this synthetic imagery as of late. You've probably been scratching your head and asking why we're covering this. Well, here it is. And this is just the beginning, and a lot of work still needs to be done. But we went one step beyond the synthetic imagery of generating the meteorological parameters and the smoke production to see if we could actually generate a volcanic ash plume, which we can see here. It's represented in this area right here if you're having a hard time seeing it. But this is from a hypothetical eruption from Yellowstone, Montana, or Yellowstone, Wyoming, if we had one. We placed it during the meteorological conditions on June 28, 2010 last year, to see if using the optical properties given to us for volcanic ash, if we could actually visualize these and produce these. Now you see the clouds themselves from the thunderstorm production stuff look a little bit cartoonish, and that's going to be something that needs to be dealt with. But overall, I mean, we're seeing a pretty decent representation of what we would see in the visible wavelengths here for not only meteorologically produced thunderstorms, but also an actual volcanic ash plume. So this is something to look forward to in the future, and hopefully we'll be able to take this information, mix it with the information that we get from the high split and puff models, the dispersion models, and actually be able to produce forecast volcanic ash plumes and get good forecast data from that we can use.